Hello, my name is George Torres. I'm here to present NFDFuzz, a stateful structure-aware fuzzer for named data networking. I worked on this with my colleagues at the National Institute of Standards and Technology. For those who are not familiar with fuzzers, fuzz testing, or fuzzing, is a software testing technique that aims to automatically find bugs in computer programs. There are various types of fuzzers, each with their own upsides and downsides, but they all follow the same high-level operating principle. That is, the fuzzer generates invalid or unexpected inputs and feeds these inputs to a program under test. This program is then monitored for any errors such as crashes or memory leaks. If an error is found, the input is saved for later analysis and debugging. Fuzzing is especially useful when it's applied to software that implements network protocols or services, because the inputs, which are in this case packets, often come from untrusted users. As a testament to the effectiveness of this technique, the Google-backed OSS Fuzz initiative has so far found over 20,000 bugs in 300 widely used open source projects. However, fuzz testing has not been applied to NDN yet, and this is why we've developed NFDFuzz, the first fuzzer for the NDN forwarding daemon NFD. Fuzzing a protocol such as NDN poses some interesting challenges that we had to solve in NFDFuzz. One of the first challenges we encounter is that NDN's interest in data packets have a highly structured format based on TLVs. Therefore, a naive fuzzer that blindly mutates random bytes in the packet would most likely break the TLV structure and get rejected by NFD's parser. This means that the fuzzer must have a basic understanding of the NDN packet format and structure. So we taught NFDFuzz how to produce packets that are valid enough to be recognized by the parser, but are also invalid enough as to expose bugs in the forwarding logic. The second challenge we came across is that NDN has a stateful data plane. Therefore, the fuzzer must also be stateful. This has various implications on the design of NFDFuzz. For instance, we maintain a history of packets that were recently sent to the forwarder. So we can test unique NDN features such as retransmission suppression, intrastate matching, and content caching. We also found out that a single packet is typically insufficient to trigger a bug. So with NFDFuzz, we extended the input format to represent not just one packet, but a sequence of packets, or a packet trace. Along with multiple packets, we also have to deal with multiple faces. This is because some NDN features such as intrasaggregation and forwarding strategies need more than one input or output face to really have all of their logic tested in full. Thus, the fuzzer must maintain these faces and keep track of what face a particular packet was sent through. NFDFuzz leverages LLVM's libfuzzer as its core fuzzing engine and complements it with a two-level custom mutator. At the top level, we have a packet mutator that understands the NDN protocol semantics and makes decisions on what packet to generate next. Then the top-level mutator calls a lower-level mutator that operates on the TLV structure by randomly adding, removing, or rearranging individual TLV elements, or changing their value. We also instrument NFD and the NDN library with address sanitizer in order to more reliably catch memory errors such as out-of-bounds accesses. And we use Google's flat buffer so that we can efficiently serialize and deserialize the fuzzer's inputs, which are the packet traces plus some metadata, into the corpus, which is then stored on disk. The picture shows a very high-level overview of the main fuzzing loop. So a random input is picked from the corpus, past the mutator to be altered, and is then fed to NFD. Now, if we're lucky, NFD will crash. That means the fuzzer found a bug, which is then reported to the user for analysis and eventually fixed. But in most cases, NFD will not crash. So the fuzzer will check the code coverage analysis to see if that particular input discovered new execution paths in the code. If that is the case, the input is saved into the corpus so that it can be further mutated in future iterations. This process is repeated until a bug is detected. NFDFuzz is still a work in progress, but preliminary results are very promising. The fuzzer found 4 bugs in NFD in just a few hours of testing. Future work includes expanding coverage to include NFD management, the NDN link protocol, and NAC. We also want to try other fuzzing engines such as AFL++, HongFuzz, and we're looking into investigating a hybrid approach for packet generation and mutation to see if we can expand coverage in a meaningful way. Thank you for your time and attention.